Good morning. Today, after developing that whole bracket symbolism, I feel that we should go ahead and drop all pretense about what's really going on here. Everything that we were talking about is based on these algebra rules for these bracket quantities. The a, the b, and the alpha in the third formula, that is, are real numbers. Before we drop all pretense, I want to think about motivations. If you had an individual named Zeke, and Zeke knew only about the integers, hence the z, Zeke would say to you, 3x equals 7 has no solutions, and within his context he would be right. Rachel, who knows all about rational numbers, though, would say, on the contrary, 3x equals 7 does have a solution. X is 7 over 3. Zeke's response initially might very well be, I don't know what you're talking about. This isn't even a number. The only numbers there are things like -3 and 1 and 2 and 0 and that sort of thing. Rachel could rejoin by saying, this is just that first game we were playing, the open parentheses AB close parentheses business, and we've decided to write the ordered pairs in this form so that we don't have to write so much. Having done that, there are certain rules of arithmetic that follow almost immediately. I imagine that Zeke would be grumbling for some time, but eventually would come to grips with it. Rachel's friend Quinn, who also knows all about rational numbers, but no other type, would happily agree that the equation x squared equals 4 has two solutions. However, he'll claim that x squared minus 5 has none because there is no rational number that you can square and obtain 5 for an answer. In the bracket notation, we decided how we would do addition. Bracket a comma b is bracket a comma 0 plus bracket 0 comma b. We've decided that we're going to identify things with a 0 in the second slot as just being a real number. So instead of literally writing bracket a comma 0, I'm just going to write a instead. But by way of contrast, that thing is not one of those things. This thing cannot be associated with any real number. There is no place on the real number line that I can associate with 0, 1. These other type of numbers do have a very interesting behavior, though. If I take 0, 1 and square it, if I multiply it by itself, using the recipes that we've previously established, I end up with something with a -1 in the first position and a 0 in the second position. We associate that with a real number. To be exact, the real number -1. The bracket number system contains a number whose square is -1. The initial response to that is to say there isn't any such thing, and this is just being silly. This is the same answer that Zeke gave when he said that 3x equals 7 has no solutions. This is the same answer that Quinn said when he said x squared minus 5 doesn't have any solutions. The thought is, we're going to have the real number system, and we're going to append to it stuff that has a non-zero number in that second bracket, things that are multiples of this thing that isn't a real number. That thing has the property that when you square it, you get -1 for an answer. Just as we invented symbols that represented 7 above 3 and square root of 5, we're going to introduce a new symbol for this special number that gets multiplied by b here, the bracket quantity 0, 1. So rather than actually write these as bracket a comma b bracket, I'm now going to write this as a plus bi, with the understanding that I is one of the members of this bracket set that is not a real number. I, we've already seen, has the special property that I squared is negative 1. Our knee-jerk response is, there is no such thing, no square is negative 1. But if you looked at the two games that we played, and look at what Zeke, Rachel, and Quinn had to say, you'll see that we're exactly in their position. We've made our number system bigger. It's now possible to do things that were not possible before. I want to be very explicit here about the connection between the way we did arithmetic in the bracket form and this new a plus bi form. In the bracket form, bracket a comma b plus bracket c comma d is bracket a plus c comma b plus d. What does this look like when written in our new symbolism? Bracket AB will now be written as a plus bi. Likewise, CD is c plus di. Never mind any mechanical manipulations. This is the number a plus c plus that number b plus d times I. When written in this format, it looks very much like we're just doing ordinary algebra where I is a variable. Something exactly similar happens for subtraction and multiplication by a real. This rule, if I think of my AB brackets as a plus bi, literally is the distributive law. It looks as though we might run into a snag on multiplication, but let's play yet another game. We saw earlier in addition, subtraction, and multiplication by a real that these I quantities basically acted as though they were just algebra variables. Let's take that line of reasoning and run with it. If I is treated just as an ordinary variable, like in a polynomial, let's figure out what this would be just by doing the FOIL method. In the context that we are working in, though, I squared is negative 1. This last term is b times d times negative 1. That's a real number, which I can combine like terms with. This term, the other two terms have a factor of I, so we'll group those together as well. Doing the arithmetic and combining like terms, I get AC minus BD plus AD plus BCI. I can transition from the bracket notation to the A plus BI notation just by pretending that I is an ordinary algebra variable, except it has the special property that when you square it, you get negative 1. Having established that, routine calculations can now be done. In a problem of this nature, I'm just going to pretend that I is a variable and do ordinary algebra on it, remembering, though, that I squared is negative 1. Multiplication is no harder, and as you'll remember, if I know how to do multiplication, I know how to do division as well. We can check and make sure that this is right by multiplying the answer by 2 plus 5i, and making sure that we get back 3 plus 2i as we're supposed to. Pretending that this is just ordinary algebra, with the understanding I squared is negative 1, after all the arithmetic is done, we end up with 3 plus 2i just as we're supposed to. If z is a number of this type, which we'll call a complex number, then a is the real part of z, b is the imaginary part. We'll sometimes write that as re of z, real of z, is a, and imaginary part of z is b. It's very important that you don't think that the imaginary part is b times I. The standard terminology has the imaginary part is the coefficient of the I. Z conjugate will be a minus b times I, and z times z conjugate is a squared plus b squared. It will sometimes be useful to think of these complex numbers as being almost like the vectors that you studied in calculus. The z could be an arrow drawn from the origin to the real x-coordinate a and real y-coordinate b. Because of the Pythagorean theorem, the length of that vector would be radical a squared plus b squared. This symbol is usually pronounced the modulus of z. It's just the length of this arrow, though. In a way that's very similar to what went on in vector calculus, I can think of a plus bi in another way. I can think of the a as being the modulus of z times the cosine of the angle that this arrow makes with the positive x-axis, and I can think of b as being modulus z times sine of that angle. If I think of it that way, then z could also be written, a plus bi could also be written modulus z cosine theta plus modulus z sine theta I. Just as with vector calculus, I can rewrite this yet another way. This number just tells me the length of this arrow, the modulus of the complex number, but has absolutely nothing to do with which direction the arrow in the picture is pointing in. This quantity is a complex number. In our earlier work, we would have thought of it as a vector, but now it's a complex number. Cosine theta plus I sine theta. As we'll show in just a moment, that complex number always has modulus 1, so it is really very much like the polar decomposition for vectors. Length of the arrow times a quantity that has nothing to do with the length but does tell you about the direction. Keeping firmly in your mind that the imaginary part of cosine theta plus I sine theta is sine theta, not I sine theta. If I square the real part, square the imaginary part, add them and do the principal square root, I get 1, just as I should. A person might be forgiven for thinking that all of this and all it's ever going to amount to is a fancied up version of vector calculations. But these things have a structure that vectors didn't have. In vector calculations, we had a product called the dot product. We had another product called the cross product. But unlike either one of those things, we have a new product on these complex numbers. So let's look into that. Think of having a complex number, z. Z is the modulus of z times the complex number cosine alpha plus I sine alpha. Alpha is the angle between the arrow that goes with the z number and the positive x-axis. Likewise, w is the number, the real number, length of w, times the complex number cosine beta plus I sine beta, where beta is the angle between the positive x-axis and our little arrow that would represent the w complex number. I want to multiply these two things together and see what I get. It's right at this moment that we depart from the vector idea. If you look back in vector calculations, we had no analog to this kind of thing. If you'll remember from trigonometry, we have a massive pile of trig identities which are going to help us simplify these two expressions. This complex number has its real part cosine of some angle and its imaginary part sine of that same angle. The complex number inside the parentheses has modulus 1. This is a real number, so is that one. The product is a real number. Complex number z times w is the length of z times the length of w times one of these cosine of an angle plus I sine of the same angle complex numbers. The length of z times w is the length of z times the length of w, and the angle that z times w makes with the positive x-axis is the sum of the angles that the two original complex numbers made. This is new. There's no analog to this structure in ordinary vector calculus. As a prelude of things to come, I want to calculate the cube roots of unity. There are several different ways I could go about this. I'm going to be absolutely literal-minded about it, though. I'm looking for a complex number z, which I could write as a plus bi, so that z cubed is 1. The modulus of z cubed is 1. The modulus of z cubed is 1. Modulus of z must be 1. When I multiply z by itself, the angle that goes with z squared will be 2 times the angle that went with z. When I calculate z cubed, which is z times z squared, I'll take twice the angle that went with z and add in the angle that goes with z. A complex number with modulus 1 and angle alpha is going to have cube equal to cosine of 3 alpha plus I sine of 3 alpha. It's worth mentioning that if either one of those two numbers, cosine 3 alpha or sine of 3 alpha, is 1 or negative 1, the other one has to be 0 automatically because of ordinary trig identities. So if I want this to work out the way that I want it to work out, it's going to be necessary that cosine of 3 times alpha needs to be of 1. So z cubed is going to be cosine of 3 alpha plus I sine of 3 alpha. I'm trying to find all cube roots of 1, so I want z cubed to come up equal to 1. That means the imaginary part needs to be 0. That means that 3 alpha must be a multiple of pi, but I have to be a little bit careful about this. Some multiples of pi will make the cosine take on value negative 1 instead of 1, so let's be careful and investigate this. I can see that I'm going to have an interesting situation when alpha is 0, when alpha is 2 pi over 3, and when alpha is 4 pi over 3. The other values don't give me what I'm after. They don't make z cubed equal to 1. They would make it equal to negative 1 instead. So, evaluating the trig functions, it looks like 1 has 3 cube roots. It looks like z equal 1 would work, which it obviously will, but it also looks like negative 1/2 plus radical 3 over 2i would work, and it also looks like negative 1/2 minus radical 3 over 2i would work as well. It is not obvious, just looking at it, that that's the case. I'm going to check the one in the middle, but before I do that, I want to go off and draw a little picture of where these cube roots are located at. Z equal 1 is obviously located there. The next one is one of these z numbers that has modulus 1. Its real part is negative 1/2. Its imaginary part's radical 3 over 2, which is positive, so this second one is there. The third one is the same as the second one, except the imaginary part has opposite sign, so it would be there. It looks as though the cube roots of unity are evenly spaced around the unit circle, with one of them being at the usual cube root of 1. I'm going to check that one. After I do that, you could go off and check this one too, but unless we've made a logical mistake someplace, this has to work. First, I'll need to calculate z squared, which I'll do by using the FOIL method from algebra and remembering later that I squared is negative 1. Z squared is negative 1/2 minus radical 3 over 2i. To get z cubed, I'll multiply that result by z. I have to be very careful about all of these negative signs because it would be easy to get confused. I'm going to factor a negative 1 out of this bit, and also I believe it will help me some if I factor a negative 1 out of that bit. This factor of negative 1 multiplied by that one gives me a factor of 1, which I can stop writing down. In what remains, I have two factors. Each factor contains two terms, and within each term, there is a factor of 1/2. I'm going to factor a 1/2 out of this factor, and also factor it out of that one. This is purely to make the algebra easier. This complex number, though, 1 minus radical 3i, is the complex conjugate of 1 plus radical 3i. I already know, based on what we've done before, is when I multiply those two complex numbers together, I'm going to get the real part squared plus the imaginary part squared. And again, I have to emphasize, the imaginary part is the coefficient of the I, not the number times I. After doing the arithmetic, I find out that if z is negative 1/2 plus radical 3 over 2i, then z cubed is 1. That says that this complex number is a cube root of 1. If you check the other one that we listed, you'll find out that it works too. Number 1 in the real number system only has one cube root, but in the complex number system, it has 3 of them. This is sort of an omen of things to come. But I think this has gone on long enough for one lecture, so I'm going to stop here and we'll resume pretty soon. In the meantime, I hope everybody has a good day, and I'll talk to you again soon.